Hello students, welcome back. Let's go to problem 2. A poll was conducted to 1,500 randomly selected adults in the DFW region. It found 62.0% of employed adults used internet or email on their jobs. And this problem corresponds to this problem here. And this is by Pew Internet Search, and this is from the real poll result. And this is a setting I made up. However, this one down here is far more realistic, because how do you actually end up with 62.0% to begin with? And it's coming from actually an extensive poll like this. Look at the previous problem here. From 2008 poll, Pew Internet Search found out 62%. But then again, is this correct figure, or is the real probability a little bit shifted to the left or right? It's impossible to tell. How accurate and reliable this is, that depends heavily upon the sample size. Nothing is discussed here. Now let's go back to my problem that I made up. Everything is here. Sample size, and then this is based upon the simple random sampling. So all the mathematical tools are here, and from here we can find out the confidence intervals of the real proportion. Find a 98% confidence interval of the proportion of the employed adults using internet over email of their jobs. Okay, 98% confidence interval, which means we want this kind of picture where 98% goes in the middle. Is that clear? 98% confidence interval, so there you go. And of course, 62% is the observed proportion, so it goes to the center, no problem there. What's the end? Well, that's the problem. You see, in normal picture, outline, center, end, and then shading. But in this case, in confidence interval case, you don't know the end, so just mark them as x1, x2, and you're looking for those end. So how do you get this problem done? End minus center over SE. Oh, come on. I have to do this all over again. And then let me expand the font a little bit. Approximately. Okay, end. This end, x1, minus. The center is 62%. And then over SE. But then again, what is the SE formula? It is square root of the proportion, 1 minus proportion, over the sample size. This formula here. 62%, 1 minus 62% over 1,500. Here's the computation, and here's the result. As for this formula, please remember this. This is extremely important. Whenever you have inference of proportion, you have to use this formula there. Let's go back to chapter 7, the exercise at problem. I should not have closed that window. Here it is again. In problem 2, we had two SD formulas here. Here's one, and that was for counting. And then here's the other, and that was a proportion. Previously counting, this one was for proportion. And it's the proportion that we are working on here. So this formula applies. Square root of p, 1 minus p over n. And this may very well be called the formula number 2, maybe 3. This is number 1, there's no question about that. And what's number 2? It's quite arguable this one may be number 2. So from here we can calculate the standard error, and that goes to the denominator. And let me take one more step here. Okay. All right. X1 is the quantity I'm looking for, and the z-score associated is to 1% here to the left, and that's something I can figure out from the z-table. Let's go ahead and do that. Here's my z-table, and 1% to the left. 1%, what's closest to 1%? Closest to 1%. Here we go. 0.0099, this one. This is the closest to 1%. This one is 0.0102. This one's closer. So negative 2.33. Negative 2.33. A little bit more precise computation will be negative 2.328 something. So negative 2.33 is actually pretty accurate. And then what do? You have to look up this one. So you have to flip this denominator to the other side. That's equivalent to negative 2.33 times this number. So x1 is therefore 0.662 minus of this computation, and let's figure it out using a calculator. You can punch all these in your handheld device, but let me save time. I have Mathematica with me here, so let me just copy and paste and find out like this. And there is my lower bound. 59.08% approximately speaking. 0.590799. So that's this one. And then I need the right-hand side. How do I get that? Let's change this to x2, and this is now plus, because by symmetry I have to go to the right. By symmetry I am going to the right. And as for this computation, again I'm going to use Mathematica computation. 0.6492 approximately speaking, which means 64.92% according to all that. And yeah, that's what we got. So this is the lower bound, and this is the upper bound. And as for the solution, well, here, yes, I'm using a little bit more precise computation using computer algebra system. I used z-table earlier and got 2.33, but a little bit more precise figure turns out to be 2.32635 something. So closer to 2.33, but this one's a little bit more accurate. And then if I use these figures, then we get these, eventually that, and in the end, nothing changed, as a matter of fact. Whether you use the table or a little bit better method using computer algebra system, in the end, I got the same answer as before. Even if you get two different answers using some rounding, I'm gonna count everything with full credit, so don't worry too much about it. My MATLAB, what can I say? My MATLAB sucks, but you don't have much choice in that because that's the best one we still have. with some better AI skill, hopefully we may get some better computer grader, but at this moment we are stuck there. Okay, we have enough time for the next problem. Let's go for 95% lower confidence bound. So we want 5% to the left and 95% to the right because we are looking for lower confidence bound like this. 5% here, 95% there. See, previously we had two wings, left and right, and then we had center portion. That's because we were looking for confidence intervals. And the confidence interval had lower bound and upper bound. And lower confidence bound is not the lower bound of the confidence interval. You see, this one here, this one is the lower bound of the confidence interval. It's the lower bound, and this is the upper bound. Now, upper confidence bound and lower confidence bound, they are different. They are not coming from the symmetric shading. Oops. They are coming from asymmetric shading like this. 5% here, 95% there. So 95% lower confidence bound, 95% is a majority, and lower part is 5%. How do I get that? Z-score is end minus center over SE, and SE computation is something we did before. Square root of P, 1 minus P over N, and 62%, 1 minus 62% over 1,500, and then square root. It's going to be this quantity here, and that goes to the denominator. Let me expand the font a little bit. And that should be approximately equal to the z-score associated is to 5% to the left, negative 1.645. I just happen to remember that figure. Let's see. 5% to the left. So where's 5%? Right here. 0.0505 versus 0.0495, negative 1.6, and then between these two, negative 1.645, and that's what we have. And looking for this x value, that's not too bad. Flip this denominator to the other side. And times the standard error. And then keep calculating. Flip this one over to the other side as well. Flip this one to the other side as well. This is what we get. And then this computation yields. Let's put some space in between. And let's do this computation using Wolfram Mathematica. And I'm getting 0.5999 something, about 0.60, 60%. And that's got to be the conclusion. Well, here I used 0.599, that's okay. But if you use 0.60 or 60%, I'll take it with full credit. Here's a little bit more accurate computation using a little bit more accurate z-score. Instead of 1.65, 1.64485 is used. A little bit better figure, but in the end, pretty similar result as before. And that's how you can handle confidence intervals and confidence bound for proportions. And here we use this polling on use of internet, but in the election season you have all kind of pollings going on, and all those merge to this particular topic.